Okay, welcome to chapter 5. This is lesson 4, covering section 6, the law of cosines. This is the last section of chapter 5. We'll be looking at deriving the law of cosines, solving triangles using the law of cosines. We'll look at two additional area of a triangle formula, and then there will be an opportunity for you to try applying the law of cosines on your own. Why do we care about the law of cosines? It's an important extension of the Pythagorean theorem. Specifically, the law of cosines works for any triangle, not just right triangles. So let's see if we can derive the law of cosines in a way that makes sense. A lot of times you're just given the law of cosines, but I think it helps to see where it comes from. So we're going to start with a triangle. Here we have triangle ABC, where side A is across from angle A. So side A is in red, and then that side has been extended into 2 dimensions. So that's a square, A by A. And then same thing, we have angle B. Across from angle B is side B, and off of side B is the square that has area B by B. And then same thing for angle and side C. And what we're going to do is construct altitudes from each of these angles. So from angle A, the altitude is already drawn in. It goes through side A at a right angle. And then I just continued that altitude all the way through the square. From angle B, we'll do the same thing. Altitude perpendicular to side B. And then from angle C, creating an altitude perpendicularly through side C. So what I want to focus on first is the altitude that was drawn in first. So I'm going to clear off some of these notations here. And we're going to look at first these 2 triangles here to see if we can solve for x and y. So first I'm going to draw in this triangle, and then we will solve also this triangle. And I'll color coordinate the sides so that we can see this is side B. This is side length C. And then side A has actually been broken into 2 pieces. This is X and Y. And because this was built by an altitude, we also know that these are right angles. The angle here between the red and green is angle B. And the angle here between red and blue is angle C. So what I'd like to do first, we know this is side length C and side length B. Let's try solving for X first. So if I'm looking at this triangle, I have angle B, I have the hypotenuse, and I have the side length adjacent to B. So I have the adjacent and the hypotenuse. I know I can use cosine to set up an equation. Cosine of angle B equals adjacent over hypotenuse, which gives us that x equals c times cosine of b. So we know that the length of x is c times cosine of b. We'll do the same thing for y. We have angle C, we have the hypotenuse, which is b, and we have the adjacent side. So again, we're going to use cosine. Cosine of c equals adjacent, that's y, over the hypotenuse, which is b. Then y equals b times cosine of c. B times cosine of c. So to find the area of the rectangle here created by the altitude and the square that's red, what we can do is we can fill in the area by multiplying a times x. So we know that the area here is a times c times cosine of b. And then we know the area of the second part of the square there, the second rectangle, is going to be, again, dimension a times y. So that's a times b times cosine cosine of C. Okay, now we can do this same process and find the area of each of these 6 rectangles. And you can feel free to kind of go through that process, but what I'm going to do is skip ahead and kind of clean up this triangle and fill in all of those areas. Okay, so what I want you to notice here is a relationship. Notice the 2 areas that are next to each other but in opposite squares. So here we have A times C times cosine of B. The adjacent but not same square rectangle. So the rectangle that's next to it but not in the same square, not off of the same side of the triangle, has the same area, C times A times cosine of B. Because multiplication is commutative, C times A and A times C are the same. And we can see that happens for all 3 of these sides. And that's the foundation for where the law of cosines comes from. So if I wanted to find, let's say, a squared, and that's the red one. So if I want to find a squared, I can say, well, that's a squared is b squared plus c squared. That should look familiar, like Pythagorean theorem, except if I take b squared plus c squared, b squared is b times a times cosine of c plus b times c times cosine of a plus c squared, that's the green one, is c times a times cosine of b. So see, I'm adding up all the little rectangles, c times b times cosine of a. And a squared is just a times c times cosine of b plus a times b times cosine of c. And so I have here a times c times cosine of b and a times b times cosine of c. These are extra. So I have to subtract then 2bc cosine of a. And now I have an equality. Okay, so I actually had to subtract out these 2 red rectangles here. Now that's the one that we kind of built up, but we can do the same thing for any of our side lengths. So I can also have b squared equals a squared plus c squared, but then I have to subtract, side B is blue, I have to subtract the 2 blue rectangles, 2ac cosine of b. Okay, so let's look at the pattern here. If I look at where my a's are, my a's are on the same side of the equal sign, my c's are on the same side of the equal sign, my b's are on the opposite side of the equal sign, and one of them is an angle. Okay, so we start out with Pythagorean theorem, c squared equals a squared plus b squared, but then we have to subtract the extras because this is not a right triangle. So then we have to subtract out 2ab from the same side of the equation times cosine of the variable that we have solved for on the other side of the equation, but as the angle. Okay, and that is the law of cosines. So I'm going to put them up here officially. The law of cosines, if triangle ABC is any triangle with sides and angles labeled in the usual way, then we have these 3 equations that we can use to solve for any side or any angle as long as we're given 3 pieces of the triangle. Okay, let's apply this. So we have triangle ABC. We have A equals 10, B equals 4, and angle C equals 25 degrees. Now, you might ask yourself, why don't we use law of sines for this? Notice we don't have any pair of angle and side that correspond to the same variable, right? I have side A, side B, and angle C. That's your hint that you have to use law of cosines, okay? If I had side A and angle A, then we can use law of sines because that gives me one of my ratios. But if I have one of each variable, an A, a B, and a C, and one of them could be an angle or all three could be sides, then I have to use law of cosines. So I'm going to go ahead and draw kind of a generic triangle here. A, B, C. This is not going to be to scale. This is just going to give us some diagram that we can label. Side A is 10, side B is 4, angle C is 25 degrees. What we need to do is find side C. So we'll have C equals, and then we need to find angle A and angle B in order to finish solving this triangle. And then we'll have all six variables labeled, okay? So it doesn't really matter which one we start with. Let's go ahead and start with side C. So in order to find side C, I want to use the law of cosines that solves for side C. So that's C squared equals A squared plus B squared minus 2AB cosine of C. And then we're just going to plug and chug because it's already isolated the variable that we want to find. C squared equals A is 10 squared plus B is 4 squared minus 2 times 10 times 4 times cosine of 25 degrees. Make sure your calculator is in degrees mode. C equals the square root of our answer directly into the calculator. And we should get that C is approximately 6.595. No units were given, so that is our value for C. If you solved before taking the square root, don't round. You want to take the square root of the exact answer, but you should have gotten the square root of 43.49537704. Never round if you don't have to. We don't have to for this. So take the square root of the answer in your calculator. Okay, so that is our value for C. Now we want to find our angles. So now that we have a value for C, technically we could use law of sines. However, we would have to use the estimated value for C. So when you don't have to, we try not to. Now, no matter what, even if we use a law of cosines, we'll still need to use the estimated value of C, but it will be more precise to do that than to estimate it into the law of sines. Additionally, the law of cosines, when we're solving for an angle, which I'll show you in a second, if we're given all three sides and we're solving for an angle, the law of cosines will always give us an angle between 0 and 180 degrees, or from 0 to pi radians, which is really nice because then we don't have to think about which quadrant we're in. Whereas the inverse of sine gives us an answer in quadrant 1 or 4 of the unit circle. So sometimes if our angle is bigger than a right angle, we have to worry about, okay, I got a negative angle measurement. What does that mean in terms of the angle in my triangle? Okay, so law of cosines will give you a more straightforward and direct answer. So let's see what that looks like. Let's solve for angle A. To solve for angle A, I want A to be inside of my cosine. So we're going to use A squared equals B squared plus C squared minus 2BC cosine of angle A. Now I want to isolate angle A, so I'm going to go ahead and rearrange this without substituting the numbers in yet. I'm going to solve for A and then substitute the numbers. That's a personal preference. If you prefer to substitute the numbers first, you can do that and you should get the same answer. But I'm going to go ahead and isolate. So that's A squared minus B squared minus C squared equals negative 2BC cosine of A. Divide by negative 2BC. And then to get A, I need to do cosine inverse. So A equals cosine inverse of A squared minus B squared minus C squared divided by negative 2BC. Substituting my values, I get cosine inverse of A was 10 minus B was 4 minus C, which is 6.595 squared, divided by negative 2 times B times C. Into the calculator that goes. Make sure you're trying this in your own calculator, because especially for things like this, the way that you type it into the calculator needs to be practiced. The whole numerator needs to be grouped together. The whole denominator needs to be grouped together. Otherwise, you'll only be dividing the 6.595 squared divided by negative 2, and then it'll be times 4 times 6.595 being subtracted from 10 squared minus 4 squared. This is something completely different, right? I don't just want to divide the last term of the numerator by the first term of the denominator. I want to divide the whole thing. So you need those parentheses. You should get 140.151 degrees. We are going to round that to 140 degrees. So angle A is 140 degrees. Lastly, we need angle B. Well, if we have two angles, we can find the third angle. We don't need the law of cosines to do that. To find our final angle, B equals 180 minus 140 minus 25. That gives us a 15-degree angle. So those were our three missing pieces. This is 15 degrees. Okay, so if I was doing law of cosines and I was given three sides and no angles, then I would have to do this process of finding the angle twice, and then I can use the triangle sum theorem to find the final angle. Okay, whenever you're doing law of cosines, you usually end up doing law of cosines twice, and then you can use the triangle sum theorem. Sometimes if you get an exact value for one of the sides, you can use law of sines the second time instead of law of cosines. But either way, you're going to use one of those laws twice before you can use the triangle sum theorem. Okay. All right. So let's look at a couple of formulas for area of a triangle. Now, I'm going to show you kind of where the first one comes from, the area of a triangle, because this one might be useful, particularly if you're doing more advanced SAT prep or something like that. This is sometimes helpful. Heron's formula you see a lot of times in higher levels of math or math competitions and things like that. Heron's formula can be useful, but we're not going to derive it together. The way that you can kind of prove Heron's formula can be complicated. So since we already proved the law of cosines from this lesson, I'm not going to prove Heron's formula. So I'm just going to show you where the area of a triangle comes from by using sine. Area of a triangle is 1/2 base times height. So if I'm looking at the base of my triangle as A, the area of my triangle is 1/2 A times the altitude H. Well, very similar to the law of cosines, where we saw that our height can be found as looking at the angle, right? So angle C, opposite is the height, hypotenuse is H. So if I have opposite and hypotenuse, I'm going to use sine. So sine of angle C equals opposite over hypotenuse. That tells me that h is b times sine of c. So that's b times sine of c. Notice this uses each variable a, b, c. Okay, so the area of this triangle is 1/2 a, b, sine of c, but I could have done that from any of the angles. So that means I could also do that as 1/2 b, c, sine of a, or I can do that as 1/2 a, c, sine of b. So all three of those work for height. Okay, we can do b sine of c as the height, c sine of b as the height, or c sine of a as the height, depending on which one we used as our base. And the important thing to note here is that it uses each of the variables one time. Very, very similar to the law of cosines, how we get that formula. Okay, Heron's formula is a little bit more complicated. It uses what's called semi-perimeter. So that means if I take the perimeter of the triangle A plus B plus C, semi means half. So a semi-perimeter is that divided by 2, kind of like a midpoint, except that we're using the lengths of the sides, 3 sides of the triangle. Okay, so if we take A plus B plus C divided by 2, Heron's formula takes that value, and then it takes that value minus one of the sides, minus this other side, and minus the last side, multiplies all of those together, and then takes the square root. Okay, so let's do an example with Heron's formula. So our first step for this is that we need to find the semi-perimeter. So to find the semi-perimeter S, we need to take each of the sides, that's 10 and 12 and 14, and then divide that by 2. So we have 10, 22, 36, divided by 2 is 18. So our area is going to be the square root of 18. And then we're going to do 18 minus 10, 18 minus 12, and 18 minus 14. So that's 8, 6, and 4. So that's 8, 6, and 4. That gives us the square root of 3,456. And if I do that in the calculator, that gives me approximately 58.8 inches. This is an area, so that is squared inches. Since units were given on this, you do need to give your answer in the correct units. Okay. The last slide here is a try this. We did a law of cosines together. This is the side case. So very similar. I already talked about this. You're given 3 sides, then you have to use the law of cosines. You can't use the law of sines. So what I want you to do is try this, and then I'll show you the answer. Okay, you don't have to find the angles in alphabetical order, but I did. So I started with angle A. If I'm looking for angle A, then I want the one that's set equal to A squared. Again, I solved for A before I substituted my values, put it into the calculator carefully. I found angle A to be 41.684 degrees. For angle B, I did the same thing, but since I had already solved for angle A, I just switched around the variables. Everywhere that there was an A, I put a B, and everywhere that there was a B, I put an A. So angle B, carefully into the calculator, was 44.288 degrees. Angle C, I used the triangle sum theorem to find 94.028 degrees. If you rounded to the nearest degree, that is absolutely okay. You would get that A is 42 degrees, B is 44 degrees, and C is 94 degrees. Okay. That is it for this section. The other document that I posted on Blackbaud is the identity summary sheet. Now you should have most of these already handwritten. So important to write them out by hand so that you can get more familiar with the patterns, but I put them all here so that they're all in one place so that you can go through your identity summary sheet and make sure that they are correct. Because there's not very many things that are worse than using the correct identity but putting it in incorrectly because that's how you remember, how you wrote it down, how you remember it. Don't take for granted that there's a lot of intricate signs, pluses and minuses. So really be careful when you're looking at these identities. Okay, this is the end of the section. This is the end of the chapter. We do have the chapter test coming up after our review day. So I'll see you in class.